Hello, everyone, and welcome to the EVN Disrupt podcast. My name is Nejdet Saturyan, and I'm the editor of the Creative Tech section here at EVN Report. My guest today was Hayk Tepanyan, the co-founder and CTO of BlueQubit, a quantum computing startup that helps companies build roadmaps for quantum adoption in their businesses. In this episode, Hayk breaks down for us what quantum computing is and how they differ from classical computers. We also spoke about how BlueQubit's platform serves as a simulator for running quantum experiments and what kind of applications quantum computers can be utilized for in the near future. Thank you for listening. Hayk, thank you so much for being with us today.
Thanks for inviting me.
Hayk, let's start with a little bit of Quantum 101. Can you tell us what is the difference between a classical computer and a quantum computer?
Yeah, sure. So a quantum computer is a device that also, just like regular computers, does some form of computation and helps us solve problems. But the big difference is that quantum computers work with qubits instead of bits. And what that means is, whereas a regular bit is a 0 or 1, and you know how our computers work, and everything deep down translates to a bunch of zeros and ones, for the quantum computer case, a qubit can be 0 and 1 at the same time. We can talk for hours about what that exactly means, but on a high level, that just translates to simply very powerful feature for quantum computers, which means that with very few qubits, you can process states and solve problems that you can't do with regular computers.
Can you try to, in sort of layman terms, paint a picture for how the computing workflow works when a qubit can be represented as 0 and 1 at the same time, something that's like tangibly more valuable than in the case of classical computing?
Yeah, for sure. So, with a regular computer, you have deep down, you have these materials that store zeros and ones on a disk or a memory chip, and then you have the CPUs working with these zeros and ones, basically turning them on or off. But with a qubit, actually, there's different ways of building a qubit, but they all deep down have the same feature that they share. Every qubit is basically some very tiny particle. It can be an ion, it can be some piece of a superconducting material, very tiny material that is isolated from the outer world, that allows it to be in a quantum state. And that quantum state is basically what allows it to be 0 and 1 at the same time and be in multiple states simultaneously. That's the building block of quantum computers. And then physicists and engineers figured out ways how to control these systems, how to apply operations on these qubits, and through those operations, you can actually perform computations.
What are some applications that really need a system like this that would make quantum computers uniquely good at solving for?
Yeah, great question. So there is a lot of applications. Pretty much any heavy compute problem that we have today can be solved with quantum computers much faster. But the most attractive and the best example that is very well known is the chemistry applications of quantum computers. And by that, I mean currently to design drugs or cure diseases or design vaccines, we have very sophisticated processes, but deep down it all boils down to basically mixing together a bunch of chemicals in a laboratory and waiting for long times and figuring out, performing tests and figuring out what this end material, end chemical does, right? And we can't simulate that process with regular computers, because when you're mixing all these molecules together, there are so many millions and billions of different combinations that these molecules can bind together and form new material. That's why we can't simply perform such computations with our laptops or even supercomputers. However, with a quantum computer, it's actually naturally well fitted for such problems, and you can easily simulate such problems on a quantum computer. And basically, you can translate a multi-year experiment that tries to discover a vaccine and involves like hundreds of researchers and $1 million facilities. All of that can be simulated inside a quantum computer within seconds. So that's why it's such a transformational technology.
Is that being used much today in computational drug discovery, or is it still mostly just GPU-based supercomputers?
So there is a lot of startups out there working on this, but the bottleneck is that the current day quantum computers are not big and stable enough yet for that particular use case. But yeah, there's being progress made. Some 20 years ago, we didn't have any quantum computers. We didn't even know if we can build a qubit. It was all a theory. But yeah, slowly different companies emerged that most of them were spin-offs from universities, and people. It all started with designing a first qubit. Having this one particle that we can measure and see how it's being in the multiple states at the same time. And then it developed from there. And now we have quantum computers that have hundreds of qubits.
Right. So you mentioned that quantum computers are maybe not quite there yet to do that kind of sort of drug discovery work. There's been a lot of both announcements and sort of debates over the current state of quantum hardware. There's been announcements of this was like the first real quantum computer and stuff. Can you just give us an idea of like where quantum computers, just the actual computers, the hardware is at today? Like where are we at with the development of quantum hardware and what are the next milestones to move forward in?
Of course, yeah, that's a great question. So again, as I was saying, some 20 years ago, we didn't even know how to build a qubit. But today we have like 30 or more companies building quantum computers. And some of the biggest tech giants are among those, like Google, IBM, Amazon, and others, because they all understand that quantum computers are the future. And if they are not investing in that technology today, they are going to be missing out in the future and next couple of years.
Mm-hmm.
In terms of where actually the quantum hardware is, yeah, if you look at the trend, basically, it all started with D-Wave some 20 years ago, that they had a very specific type of quantum computers. But then a universal quantum computer started taking off around 2015.
Mm-hmm.
And when basically Google and the likes started getting into that race. And the pivotal point was in 2019, that's 4 years ago, when Google built this quantum computer with 53 qubits. And they performed this one computation with this hardware that was not possible to reproduce with any supercomputer in the world. And they published this result in the Nature magazine. That's like one of the most
Top
highly
scientific
respected
journals. Yeah.
scientific journals out there. Exactly, and it was all over the place. Everyone was talking about it. How they called it quantum supremacy,
Right.
which
Yeah.
means they performed an experiment that was possible to do with a quantum computer that was not possible to do with regular computers. The catch is that the experiment they did was on a highly theoretical problem and not really it didn't have any commercial use case or any easily interpretable result that you can explain to an average computer user and they can understand, okay, this is what I can use a quantum computer for. So that was 2019, and after that we've come a long way. So that was 53 qubits, and now we have quantum computers that are in the order of 100 qubits or more. But yeah, it's still not there. To get to the really attractive use cases like the chemistry I was talking about, you need around like 100,000 or million qubits, and that might take 5 to 10 years.
Right. Can you speak a little bit about what that experiment showed that Google did in 2019?
In quantum computers, the language that they use is this quantum circuits, which is basically a sequence of operations that you apply on qubits. It's very similar to how regular computers work. Again, you have bits and bytes, and then you have different operations like addition, subtraction, different bitwise operations that you do on top of these bits, and then you perform computation, right? So the computation that Google did was this random circuit where they put a lot of random quantum gates together and they applied on 53 qubits. And then they get to a resulting distribution that you can sample from. Whenever you measure this system, you get a bit string of length 53 because you started with 53 qubits. And that gives you a sample from that final distribution. There is a name for it. I think it's called Port Thomas. I might be wrong here. Do not quote me on this, but or Thomas Port, one of those. Yeah, it's a very well-known distribution. But the point is that to sample from that distribution with regular computers, yeah, you would need to use the biggest supercomputer out there and keep it running for 1,000 years to get just one sample. So that's how they perform this computation that allows them to show that the quantum computer was way more advantageous than regular
Right.
computers. But again, yeah, that distribution doesn't really come up often in regular life, so you can't really use that result in any useful manner.
Right. But it was an important sort of theoretical milestone, I guess.
Exactly, yes.
Let's get a little bit into your background. You did your undergrad in Stanford, and then you were a software engineer at Google. Tell us a little bit about how you got interested into quantum and what you've been doing in the space before BlueQubit.
Of course, yeah. I guess I'll start from a bit earlier. So I went to high school in Armenia, into quantum college. At the time, I didn't know anything about quantum or quantum physics, but it was one of the best schools in Armenia. So I really loved my experience there. It's a funny thing that I
Yeah.
ended up co-founding a company in
Yeah.
quantum computing. But yeah, I learned about quantum first when I was at Stanford, and I met my current co-founder, Hrant Garibian, was doing his PhD in quantum physics there.
Mm-hmm.
And we were the only Armenians from Armenia studying at Stanford at the time. There were other Armenians as well, but most of them were from US or other places. So, and we had like a nice little Armenian community in Stanford. But yeah, me and Hrant were kind of closer friends because again, we shared a lot of same experiences coming from Armenia and going to these different math and physics Olympiads and stuff like that. So yeah, he basically taught me the basics in quantum computing, and I started like learning from there by myself. That was some 8 or 9 years ago, and yeah, that's how my love for quantum physics and quantum computing started.
Were you a computer science student or a physics student?
I was a computer science student, but I took a bunch of physics classes, and
Right.
in high school I also went to the Physics International Olympiad. So it was a big decision for me actually. Yeah, principal of Quantum College actually was convincing me all the time to go into physics and yeah, continue that path. But yeah,
Yeah.
somehow I loved computers more, and I went into computer science.
Into
But now, yeah,
computer
I
science.
kind of I'm combining both, so I have best of two worlds. So quantum
Right.
computers combines both physics and computers. So pretty
Right.
happy with that.
You have a foot in both doors. Okay, awesome. And then you end up at Google as a software engineer. Were you working on quantum tech there, or a general software engineer?
I was a general software engineer at Google. The quantum team at Google is actually pretty small. It was pretty small at the time I was there. Right now, it's actually it's getting bigger every year. But yeah, I got to Google. I got into Google at 2018. That was 5 years ago. I was in Google Ads, which is one of the most important departments at Google. We had a running joke in Google saying that Google Ads pays the bills for Google
Right.
because that's where most of the revenue for Google comes.
Right.
So even recently, when there was like a lot of layoffs at Google, Google Ads was not touched at all because yeah, like
Yeah.
they never touch something that brings
Makes
revenue.
the money. Yeah.
Yeah,
Ads is what pays for the quantum computers and the
basically,
supercomputers
yeah.
that do the AI work there. Brings up like an interesting question of how seriously the big tech companies are taking quantum now. That Google has done some really significant work in quantum. At companies like at the Googles of the world, is it still limited mostly to sort of essentially academic research being done in industry, or are there teams that are looking to implement these things into products and sort of bring them more into market? And I guess part of that would be through sort of offering quantum computing through like cloud services and things like that. But I'm also curious about outside of that, like something that would be more not even necessarily consumer facing, but like B2B applications that are not just providing compute power.
Yeah, funny that you asked that because we actually provide access to quantum computers through our platform. But yeah, it's actually yeah, mostly used by quantum R&D today. Researchers either at quantum startups or quantum companies or industry companies, enterprises that have quantum teams and quantum R&D. And the number of such companies is growing every year. Like big major banks have quantum teams like JP Morgan, Chase, Bank of America, and a lot of insurance companies and supply chain companies. Basically, again, any major company that has a lot of heavy compute problems is realizing the potential of this technology. So they are starting to thinking about how to adopt quantum computing, how to build a roadmap
Mm-hmm.
for it, how to be ready when there is a commercial quantum advantage. And yeah, they're starting to hire teams, and the demand for quantum engineers is actually growing a lot. And yeah, you can see like pretty much every company is looking for some, but yeah, there's not that many experts out there, which is where our company comes into place. So
Right.
yeah, but
So
happy to talk more about that.
let's
Yeah.
dive into BlueQubit now. Tell us what BlueQubit is and what is the problem that you guys are looking to solve.
Right. So on a high level, as I was saying, demand for quantum experts is growing, and a lot of companies are realizing the potential for quantum and are starting to build roadmaps for it. But there's not that many experts, right? So what we think is going to happen in the next few years is a lot of these industry players will try to partner with quantum software companies like ours to either understand how they can integrate quantum into their tech so that they do not miss on that race, or how to apply quantum computers to their current problems already, right? Ideally, yeah, they would like everyone would hire a team of quantum engineers, but again, there aren't that many quantum engineers in the world.
Right.
So that's why we founded BlueQubit, which is a quantum software company. So we partner with hardware providers, and we have a team of quantum engineers and regular engineers, so we can help these different businesses and mostly enterprises, again, the companies that have high compute problems, to understand how quantum can help them and where how they should be prepared for a quantum advantage when it arrives.
From a platform perspective, tell us how it is that BlueQubit like actualizes that, because my understanding is that in some ways it acts as a programming library, right, for people to be able to implement quantum into their applications. Or
It's more like a platform. So the current version of the platform that we have has some learning resources that addresses that issue I was talking about, that any team lead or a senior engineer at these companies can come and learn about, again, what the basics are and what applications quantum computing has and things like that. But on top of that, we also have tools for quantum R&D. And that's the advanced part that, again, we are offering as is, or we're also offering service where we partner with these companies and we run pilots, and we kind of basically hold their hands and walk them through different milestones of implementing different things with quantum and understanding how it works, right? And these different tools range from quantum simulators, emulators, to hybrid compute capabilities. But these are like highly technical terms, and again, these are like very well known in the quantum R&D world. But again, to learn about this, you first gotta go through the basics and understand building blocks of quantum computing.
right. Can you explain a little bit more? I know it's hard to do in layman's terms, but can you explain a little bit more about what you mean when you say a quantum simulator?
Yeah, of course. So, as I was saying, quantum computers have this exponential power that comes from qubits, right? That can be 0 and 1 at the same time. This means that when you have, again, 50 or 100 qubits, it's really hard to, again, replicate a computation that can be done on a quantum computer. And that's essentially what the quantum supremacy was all about, right? 53 qubits. But below those numbers, like 10, 20, 30 qubit programs, those things can be simulated with regular computers and, for example, my laptop or some AWS machine. And the job of the quantum simulator is just that, to run a quantum program on a regular computer. And this is super important, again, for quantum R&D, because before sending your actual quantum algorithm to a quantum hardware, you first want to like test it out, debug it, and run it a bunch of times on your laptop or on a quantum simulator in the cloud. And then once you figure out that everything is ready, well written, then you can send it to an actual quantum hardware. That's why quantum simulators are so important today. But we think that also they're going to keep being important in the future as well, because even when we do have like large scale stable quantum computers, at least in the beginning stages, it's going to be very expensive. It's going to be very scarce resource. So a lot of time, again, you'll have to first test, experiment your programs on a simulator first, and then submit them to the quantum hardware.
These companies that you said you guys are partnering up with to help them show how they can incorporate quantum into their workflows, can you give us a little bit more? I know I'm sure you can't speak about specifics of what your customers are working on with it, but can you speak a little bit more in general terms, some use cases that they're exploring with quantum?
Yeah, definitely. So, for example, one of the pilots we're working on now, again, without going into specifics, we're looking into, again, a very on a high level, very compute heavy problem. It's a risk modeling problem where basically we have this insurance company that is trying to quantify the risk that they are dealing with when they are dealing with their users. And because they have, again, thousands, hundreds of thousands of users, and they have these huge amounts of data, there's all kinds of different business questions that you can ask about this data that are super important for the life of the business, right? And the current solutions in these cases might be just running a bunch of supercomputers for hours or days to try to figure out some remotely accurate solutions. But with the help of the right quantum hardware, you can do such things in a matter of seconds in a more accurate way. That's one of the most common use cases. In general, just one more thing, as I was saying, like chemistry is the most attractive use case, but that requires a lot of qubits. Before getting to chemistry applications, the optimization problems are what a lot of quantum R&D companies are working on. And this particular example I just brought about risk modeling is also just an example of an optimization problem, basically.
And they're using your platform to essentially like test out how well that would work through your simulators before deploying it to a full scale quantum computer.
Yeah,
Is that correct?
yes, correct. Yeah, right now it's actually more like building a roadmap of understanding like exactly how many qubits you need to
Right.
achieve specific level of performance. There isn't really a production grade quantum hardware again yet. Even if we get like excellent results on our platform, we can't really hope to deploy it today. But yeah, it's entirely possible that in a few years we'll get to a point where those solutions can be deployed in production.
So right now it's the people that would be using your simulators, it would mostly be for in order to like understand what they would be able to do in the future to be ready for when that time comes.
Yeah, exactly. So that one nice thing about the simulators also is that if you build your infra with that simulator in mind and you build all of your algorithms in place with that, once you have actual quantum hardware, it's very simple to just replace your simulator with the quantum hardware and just run your program on that. A lot of companies ask us, like when quantum computers are here, we'll just kind of translate our code from whatever we have to quantum, right? Isn't that easy? But that's not really the case. It's not like going from Python to C++ or
Right.
from Java to C++, because it's a totally different paradigm. It requires a totally different approach and different set of algorithms, so it takes a lot of time and effort to actually design these things. And that's basically what BlueQubit helps its clients to do.
How much interest are you guys seeing in the market for something that I guess it'd be interesting to see, like, as the demand for products like this grow, it really shows that big players like big financial institutions and the other examples that you mentioned are really waiting for the breakthrough in quantum so that they can deploy those solutions, right?
Yeah, so it's actually, if you look at the big picture, it's like a top-down adoption that we're seeing. Like the major banks that have longer time horizons, that are actually like thinking about like 5, 10 year plans. Those are the first companies that started adopting quantum teams some 5 years ago, and then it started from there. Now you have like regional banks and medium-sized companies also adopting this approach. But yeah, it's not really getting to these SMBs and medium-sized businesses yet. Yet those folks have like higher priority fires to fight, these days. So yeah, you can't really
Right, for
pitch them
sure.
a quantum solution these days. Yeah.
It's a bit of a luxury for
Yeah,
them. Yeah.
exactly.
What about for non-business solutions? Like from just like a purely like research perspective, is BlueQubit a platform that could be used by like academics for like experimentation and for R&D work?
Yeah, definitely. Again, as most of our team are quantum physics PhDs and scientists, and that's how we know that what features and tools could be useful to build. Some, again, part of our team is also working on quantum R&D themselves. And some of those results can be applied, have some business application, but some are actually like research results. The tools that are used in quantum R&D in universities and in academia are also very similar to the ones that I was mentioning, like simulators and hybrid compute and things like that. We actually have a couple of advisors from major universities like University of Chicago, Stanford, who are advising us, and their groups of students are also looking into using BlueQubit for their research projects as well.
It's fantastic. I imagine it also applies to research disciplines outside of quantum. For instance, over the last few years, there's been some noise made about like quantum machine learning and how that might be a new paradigm in AI research. Is that an avenue you guys are exploring as well for the scientific research side?
Yeah, definitely. Actually, just today morning, actually, I got off a call with one of our quantum ML engineers, and there's actually right now a project we are doing that is one of the, again, cutting edge, newest revelations in that field. I would love to go more into that. Not sure if such technical details would be appropriate
Yeah,
for this
absolutely.
format,
Yeah.
but
No, go
yeah,
for it. Yeah.
awesome. That's awesome. Yeah, I love talking about this. So we're working on this basically thing called variational circuits, and the way it works is it's again on a high level. It's a combination of quantum computing and traditional machine learning. What I mean by that is basically you're training your quantum circuit and you're learning parameters of your circuit, trying to achieve some goal, right? In a traditional machine learning setting, you have a problem, you have data, you train your model on the data to achieve a low score and solve your problem, right? You have your optimization function that you are optimizing. This is a machine learning slash neural network setup. So in our setup, we have a quantum circuit. We don't have the problem setup is such that we're trying to build a quantum circuit which prepares a specific state. This is basically the first step in any quantum program, preparing your desired state. Remember, I was saying a qubit can be both 0 and 1 at the same time. If you have 20 qubits, it can be in a combination of a million different states. So everything revolves around these states, right, in a quantum world. And basically, any computation you do is you start from one state and you perform some actions and you end up in another state, and that's your solution, right? So, for example, you start with all zero state and then you perform computations to end up in a state that corresponds to the minimal solution for your problem. One of the most important steps in this whole process is preparing your initial state, which is the same as kind of encoding your problem into a quantum computer. And to tackle that problem, we're using this quantum ML approach where we are fixing the circuit and we are learning different parameters that are going into the circuit, kind of like machine learning style, where we have a objective function that we're optimizing by doing multiple runs. And again, we're extensively using simulators for this. On a typical day, we might run like 100,000 simulations for some 20 qubit circuit to converge to this specific quantum program that can prepare the state that we desire. So yeah, it's pretty amazing stuff.
It's kind of like an
Yeah.
underlying optimization for the quantum computing setup, I guess.
Yeah, kinda. So in any quantum program you're gonna have these three stages basically: state preparation, problem computation, and then measurement. The measurement step is where you extract your answer from the quantum computer. You know, as I was saying, you can, again, with 20 qubits, you can be in a million different states. But the catch is whenever you measure this quantum device, you only get one of those million states. So if you measure it a million times, you're going to get a million different results. But that's how you kind of can infer some information about the internal state of the quantum computer, right? So again, it's state preparation, computation, and measurement. So what we are doing now is tackling this first stage of this whole process, which is again inseparable part of any quantum program, the state preparation, also known as data loading, because state preparation is similar to you are encoding your problem into the quantum computer. So yeah, this specific branch of research that we're engaged in now is tackling that problem.
Right. So let's get a little bit more into sort of the R&D work you guys. I'm more curious about some of your R&D ambitions and how it might tie into your presence in Armenia. So Armenia is known to have definitely a strong like math background and has had strong physics programs at times. I think right now the state of science in Armenia in general is something that has been spoken a lot about of being in need for improvement and much more investment. How do you guys see your role in sort of developing the capacity to be able to do quantum research in Armenia? Is that something that's in the works for BlueQubit?
Currently, most of our teammates at Armenia are engineers, but we do have actually people with physics background and with PhDs in physics. Actually, our head of engineering is also a Stanford alumni who decided to move back and continue his career in Armenia, which is awesome. And he's our old friend. We knew him for like multiple years. So we were really happy when he decided to join us. So he's heading the engineering team, and he's also working on the quantum R&D part. In terms of a bigger picture, how we are thinking about research in Armenia, we're actually planning to start either this year or next year, we'll start some educational courses on quantum computing. Currently, there's some universities offering courses in. So quantum physics has been around for multiple years in Yerevan State University. You can study quantum physics, no problem. But quantum computing is this emerging tech that's really rare to find. That's why I was saying there's not that many experts in it. It's kind of in the intersection of math, physics, quantum physics, computer science, statistics. So you need like linear algebra. So you need a lot of background to kind of understand what's going on in there. But yeah, we're thinking about starting courses in quantum computing in Armenia that will be open for basically university students, and everyone should be able to apply. And we are also working on establishing relationships with the current teams in Slavonic University, the Yerevan State University, that have teams working in quantum computing. So that whole effort is not just a BlueQubit effort, but it's a joint project. So everyone can see what's going on, and the students also have multiple options after the course to either go to research in a university, or maybe join BlueQubit, or maybe start their own quantum computing startup. Who knows?
Right. That's fantastic. And it seems like we sort of have the necessary foundations that you were mentioning. It seems like Armenia already has a lot of those. There's something to really build on top of.
Yeah, Armenia has a really long history of, again, natural sciences, like strong people in physics and math. Again, quantum computing is like a pretty new field, so we still have to see how that goes. But yeah, the background, the foundation is definitely there. So yeah.
It's fantastic. Okay, Hayk Can, my last question, sort of our traditional last question is, where do you hope to see BlueQubit in the coming 5 years? What do you guys hope to be achieving in 5 years?
5 years, we hope to grow the team and have a more mature product that is actually adding value to its customers and is leveraging by then existing stable quantum computers to solve really important problems in the world.
Fantastic. Hayk, thank you so much for being with us today. I think you gave us all a lot of things to Google, and I know it's a topic that's not always easy to convey in terms that everybody will understand. So I really appreciate your time with us today. Thank you so much.
Thank you.